All right. Today, we are cracking the code on a software weakness that is, well, it's shockingly simple, but incredibly powerful. It's like a secret passage hidden in plain sight, one that attackers use to break into systems every single day. So, let me ask you a question. What do you think is the single most dangerous piece of punctuation in all of programming? It's not some obscure symbol, nothing you've never heard of. It's actually something you see all the time, hiding right there in front of us. And the answer is the ... Yep, this little sequence, just a couple of dots and a slash, is the key that attackers use to unlock doors that are absolutely supposed to stay sealed shut. Now, to really get how this works, we first have to understand how things are supposed to work. Let's take a look at the digital safe that programs are designed to live inside of. This safe space has a technical name. It's called a restricted directory. And the idea is really straightforward. A program, like a web app, gets its own specific folder to work in. It can read and write files inside that folder, but it should never, under any circumstances, be allowed to wander outside of it. The perfect analogy is a bank teller's cash drawer. They have everything they need right there in their workspace to do their job, but they can't just decide to take a stroll into the main vault and grab whatever they want. The whole system is designed to keep them in their lane. But what happens when an attacker finds a way to pick the lock? Let's explore the secret passage they use to escape this digital safe. And this is where it all starts. Look at the left side. That's a normal, harmless request asking for a file called report.pdf. But on the right, that's the attack. An attacker just replaces that file name with a malicious string of ... slashes. They're not asking for a file anymore. They're trying to climb a ladder right out of the safe. So, how does this little escape act actually work? Let's walk through it. Imagine the program starts off in its safe little directory, /users/CW/profiles. The first ... is a command that just means go up one level. So, boom, it's now in /users/CW. The next ... says go up again, which lands it in /users. You see where this is going, right? By stringing a few of these together, an attacker can climb all the way out of that restricted directory and start snooping around in really sensitive system folders. So once they're out, the real damage can begin. This is the heist. Let's look at what attackers can actually do once they have this kind of access. The damage really falls into three big categories. First, you have confidentiality. An attacker can read files they should never see, like that /etc password file, which has user account info. Second, they can go after integrity. This means they could modify or even overwrite critical system files, maybe even mess with security settings. And finally, there's availability. They could just delete essential data, crashing the whole application and locking everybody out. You know, this attack is so infamous, it even picked up a cool alias, zip slip. This happens when that malicious ... sequence is hidden inside a file name that's buried within a compressed archive, like a zip file. The server gets the file, automatically unzips it, and bam, the secret passage is triggered, writing a malicious file way outside of the folder it was supposed to go into. Okay, so we've seen the problem, and it's pretty scary. Now, how do we fix it? Let's talk about building the digital defenses that can seal this secret passage for good. The thing is, these fixes are really well known, but they sometimes get overlooked when people are in a rush to build new things. The single most important rule for any developer, and this comes straight from security experts, is this one right here. Assume all input is malicious. It means anything a user sends your application, a file name, a username, you name it, you have to treat it like it's a potential attack. So how do you actually validate that input? Well, you have two main strategies. The risky way is a denialist, where you try to block a list of known bad characters, like the ... But the much safer way is an allow list. With an allow list, you only accept known good characters. You define a super strict set of characters, like maybe just A through Z and 0 through 9, and you reject literally everything else. And this is a perfect example of why those denialists are so risky. An attacker could send a clever little string like this one, ... A simple security filter might see the ... in the middle and remove it, thinking, okay, job done. But look what's left behind. The remaining characters just collapse to form a new ... The filter is completely bypassed and the attacker is in. So the game plan for any developer is to stick to these best practices. First, use that strict allow list validation. Second, and this is huge, never, ever trust a file name that a user gives you directly. And third, use the built-in functions in your programming language that are made for this, like RealPath in C or getCanonicalPath in Java. These functions are literally designed to resolve file paths safely, and they automatically neutralize any // sequences, making them totally harmless. Now, you might be sitting there thinking, okay, this is an old trick, right? Surely modern software has this all figured out by now. But, well, let's look at why this timeless threat is still so effective today. A quick look at the timeline here shows you just how persistent this thing is. Way back in 2002, a web server was getting crashed with this exact technique. Fast forward to 2019, a popular Python tool was tricked into reading sensitive files. And just in 2024, even a cutting-edge AI management tool was exploited using the very same .. method. So from simple websites to complex AI, this vulnerability just isn't going away. So if you take away just one single thing from all of this, let it be this. Never, ever trust user input. Think of it as the digital front door to your house, and attackers are constantly, relentlessly trying to find a way to pick the lock. Which kind of leads us to our final thought here. The defenses we talked about, like using allow lists and special functions, are well known, and they're relatively simple to put in place. So why? Why does this secret passage, this ancient trick, keep reappearing in our most modern software?